Hi everyone, I'm Mina. I am a postdoc at Cornell University working on programmable networks and programmable data planes. Today, Elie's gonna tell us about how to offload some media processing to programmable switches. He's a second-year PhD student at South Carolina University working on programmable switches and high-speed networking. Elie, take it away.
Thank you. So hello everybody, my name is Elie, and I'll be presenting today the offloading media traffic to P4 programmable data plane switches. And this work was sponsored by NSF, and I would like also to thank Vladimir Gurovich from Barefoot for his insightful feedback on various technical issues. So I will go over the agenda. First, I will introduce voice over IP, media traffic in general, then give some background on the protocols such as the session initiation protocol, SIP, real-time protocol, RTP. Then I will go over the problem of NAT, or the network address penetration, a little background on P4 switches, and then I will introduce the solution. I will show also some evaluation results, and I will conclude with some lessons that we learned while implementing this project. According to some estimations, 80% of the internet traffic is media, and a very large percentage of this traffic is generated by end users communicating with each other. And media services often are voice and video. They run alongside the data network in campus networks. When we talk about voice and video, so we have open solutions and proprietary solutions. And we all know that such solutions are widely used today. We have Skype, WhatsApp, Zoom, or some other solutions. And when we talk about voice and video, we have to always divide it into two categories: the signaling part and the media part. So for the signaling, this is where we establish and we manage the session, and we use session control protocols such as SIP or session initiation protocol. And for the media part, we have to use a protocol to transfer the media streams, can be audio or video or both, of course, between end users. And the most common one is the real-time protocol, or RTP for short. And we should make sure that there are some quality of service characteristics that we need to maintain. For example, ideally, we would need low jitter, low delay. Although packet losses are tolerated, we need very few packet losses in order to have a very good quality of service. A little bit background on signaling and media protocols. So as we said, SIP is used to initiate, maintain, and terminate multimedia sessions between endpoints. So in this figure here, we have two end users, UAC and UAS. UAC stands for the user agent client, and UAS for the user agent server. These, in fact, will be like the caller and the callee. So both of them will be generating media. And we have also a server, which is referred to as the SIP server, also has a function of a registrar. And this server will be used for initiating the session. So it will relay SIP traffic, the signaling traffic between the end devices, so that we can create the session or terminate or do some other stuff related to the signaling part. Now, once the session is established, RTP protocol will be used to transport the media streams between the devices. This is the ideal scenario. However, in real life, we know that there's a lot of NAT devices, a lot of firewalls that will block this peer-to-peer transmission between the end users. And here comes the NAT problem. So we know that NAT maps port private IP addresses to public IP addresses, and it's basically used almost everywhere, mostly in campus enterprise networks and operator networks. And this is a very good paper here that shows the NAT carrier-grade NAT deployments in the wild. So basically, the problem that NAT introduces is that it violates the end-to-end principle and produces some issues when we have end-to-end sessions. So the traversal won't work. And if you just try to set up a solution, a VoIP solution, sometimes you see that the session is established, but you don't have any voice or video. And this is all because of NAT. So specifically, NAT will prevent a user from outside the network to initiate a session. And if both users have NAT, then neither can accept a call. So how is this solved today? We use the SIP registrar server. So both these devices will register to a SIP server, and then the signaling will be relayed through the SIP server. SIP carries the IP addresses and port to be used by the RTP later for relaying media. And at the beginning of the session, so during the signaling part, the RTP traffic is still unknown. So we don't know the translated addresses yet. Now, this is a well-known problem. There are several solutions that try to address this problem. We listed here 3 of them: stun, turn, and ice. And all of these have RFCs. But essentially, most of these solutions rely on a publicly available relay server that we have to use it as a man-of-middle type. So we have to relay traffic to that relay server, and the relay server will relay to the other end. By having a relay server, we can make sure that the media traffic will flow between users no matter what, even if we have different types of NAT, symmetric NAT or others. And for example, this RFC here, the turn RFC, turn stands for traversal using relay around NAT, so it involved the server. And we will try to exploit this fact, as we will see now, with programmable switches. So how's the mechanism of a relay server? How does a relay server work? So if we look at this scenario, we have 2 end users, A and B. And we have a SIP server and a relay server. The relay server is just an intermediary device that will be used to relay traffic. And we know the SIP server will be responsible for the signaling part. User A and user B are behind NATs. So we would need to make sure that the media traffic will flow from A to B. At the beginning of the communication, the SIP will be used to establish the session. And at that time, we know that the SIP server communicates with the relay server. So therefore, the relay server will create ports, and these ports will be used to relay traffic on behalf of user A and user B. And this is why we see on the right-hand side here a table which is maintained by the relay server. And this table will have all the information needed so that it can relay traffic whenever it receives packets from one user to the other. Now, the problem is we are establishing the session here, but the relay server doesn't know yet the device and IP port. So as a result, the relay server will have to wait for at least one packet from both sides. And once it receives that packet, it will determine these translated IP addresses and ports, and then this information will be recorded in the table. So now the relay server has everything that it needs in order to relay traffic. And basically now, whenever a packet arrives to one port, it will relay it and send it from the other port to the other user. So having all this information, now the relay server can relay the traffic. A little overview on P4 switches. I'm not going to go into details because I think everybody knows all of these. But the interesting thing about P4 switches is that it allows the programmer to program the data plane and add some proprietary features such as emulating the RTP relay server. So we can parse packets, including UDP, which carries the RTP traffic. And we can do some header inspection, identify media sessions, modify fields, etc. And once the program compiles, if it can compile successfully, then it will run at line rate on the chip. So what is our proposed system? We try here to emulate the behavior of the relay server using programmable switch. This figure here shows the high-level architecture. So we have, again, user A and B behind NATs. We have a programmable switch. We have a SIP server and a relay server. And also we have an agent, which we will talk about that in the next slide. So essentially, when a packet arrives to the programmable switch, and that packet is carrying media traffic, it is first parsed by the switch, and then it will identify the session to which this packet belongs. And to do that, it will use the 5-tuple, so source and destination port, source acquisition IP, and protocol. And after that, it will replace the source IP with that of the relay server, and the source port with that which is used to receive traffic from user A. Then it needs to modify the destination IP and port so that it relates to user B. And after doing that, of course, we have to recalculate both IPv4 and UDP checksums, and then forward the packet to user B. As you can see, the system is very simple, but it exploits a very interesting fact of the behavior of the relay server. And programmable switches are designed to do such kind of simple modification of headers to improve the, the performance in general. Now, we created a custom software which we refer to as agent that learns the allocated port exchange between the SIP server and the relay. So we have an agent here, and it will learn these ports, and then it will use the 5-tuple allocated to the media session in order to construct a unique identifier, unique session identifier. After doing that, it will construct a rule, and then will install that rule into the programmable switch. That rule will contain the matching field as well as the data to be replaced once we have a match. And moreover, the agent will listen to by messages received at the server, so that when a call is steered down, it can delete the entry from the programmable switches. So as you can see, it's very simple. It's just push the rule, and it will delete the rule once the call is steered down. For the implementation, we use OpenSIPs, which is a well-known open source implementation of a SIP server. For the relay server, we use RTP proxy. RTP proxy, it's a production grade relay server that is used to relay RTP streams. On the end users, we used CP, which is also an open source traffic generator that generates SIP sessions as well as media traffic. And also we used iPerf just to generate more data and to have like background UDP traffic while we do the call, just to see how it affects the quality of service. And the programmable switch that we use is the Edgecore Wedge 100BF, which has the Tofino chip in it. And all the servers have 4 cores. The agent here will connect to the programmable switch using TCP to the management port so that it installs and removes the entries from the table. For the evaluation, we consider 2 scenarios. The first one we refer to as the server-based relay, and this is where we use the relay server to do the relaying of the media without intervention of the switch in terms of doing any modification to the packet. It's just forward. And the second one, which is the switch-based relay, and this is where we use the switch solely to relay media traffic. For the test, we generated 900 media sessions at the rate of 30 sessions per second, and the test lasted for 300 seconds. We use the G711 codec for media encoding, and it has a 160 bytes with a packetization rate of 20 milliseconds. So here we can see the 2 scenarios. So the switch-based relay is just modified the packet here and relay within the switch without going to the relay server. And the second one is where we go to the relay server to relay the traffic. To evaluate the results, we computed the quality of service metrics that are frequently computed when we evaluate media and voice over IP in general. So the first one is the delay, and the delay is the time interval starting when a packet is received from the UAC to the ingress port of the switch and ending when it's forwarded from the egress to the UAS. So by doing this, we were able to find the delay contribution of the switch and the relay server. And this graph here shows the cumulative distribution function of the delay of the server-based relay versus the switch-based relay. And as you can see in the server-based relay, we have a mean of 6.88 milliseconds and a standard deviation of 3.74, whereas in the switch-based relay, we only had 440 nanosecond delay, and the variation was very negligible, very small. We also calculated the delay variation, which is analogous to jitter, and is defined in RFC 4689. And this is calculated by taking the absolute value of the difference between the delay of consecutive packets. Also here, this is the CDF, and as you can see, with the server-based relay, we have 0.26 millisecond mean, although you can see that 20% had more than 0.5 millisecond delay variation, whereas in the switch-based relay also it was very negligible. The packet loss was also calculated, and this is the number of packets that failed to reach the destination. For this calculation, we relied on the sequence number in the RTP header. And for these stats, with the server-based relay, we witnessed very few loss rates, whereas in the switch-based relay, there was no packet loss at all. Another metric is the mean opinion score, or MOS. And this is a metric used to estimate the quality of the media session. It is standardized by the ITUT. And for the codec that we use, which is G711, the maximum that we can attain is 4.4. And here we did the experiment with various number of sessions just to see if we increase the number of sessions, if there will be some effect on the quality of service. The first one shows for 750 simultaneous sessions. Both of them achieved a 4.4, which is the highest mean opinion score for G711. With 1500 sessions, we can see that the server-based relays performance start to decrease. So we can see that some of the calls or the sessions didn't have a very good mean opinion score, whereas in the switch-based relay, we also got 4.4, the maximum. And as we increase further to 1800, you can see that the performance of the server's relay continued to deteriorate, whereas the switch-based relay has a constant mean opinion score independent of the number of sessions. I just need to note that when calculating the mean opinion score, the delay, the jitter, and all the metrics that we showed, we use the timestamps on the switch, which has a very high precision, and we just calculated from the time the packet enters from the ingress till it exits the egress to the other side of the code. So that's why we are getting these optimal values. We know that when we deploy it in the internet, there might have some other considerations, but ideally, if we are just comparing the relay-based scenario versus the switch-based scenario, you can see this is the difference that we get. Another metric is the CPU usage. Obviously, because we are relaying all the traffic from the server, the CPU of the server, when we use the switch-based relay, will go down approximately 0. Whereas when we use the server-based relay, you can see the first 30 seconds, it keeps increasing, and this is where calls are entering. But after the calls are established in the server-based relay, we have around 40 to 50% CPU usage. Whereas in the switch-based relay, as you can see, it increased a little bit because we are still using the relay server to allocate the port. But after that, it goes down because no packets are being arriving to the relay server. We also evaluated our P4 program using 2 different scenarios. So the first one is on top of the baseline switch program, the switch.p4, which implements some various features such as layer 2 and 3 functionalities, access control list, QoS, and others. And the other one is as a standalone implementation. And this table here shows the additional hardware resources used when we deploy it on these 2 different scenarios. You can see that when using a standalone program, we were able to fit 1,050,000 sessions while having additional resources to spare for other functionalities. And also on top of switch.t4, you can see the SRAM increase here, 32,000. And again, the table size here, every entry in the table corresponds to 1 media session. So essentially, we will be able to have 1,050,000 sessions here with this amount of increase in the SRAM. So what are some lessons that we learned when implementing this project? First, we can see that there's a significant performance improvement when using the switch in terms of quality of service and in terms of the number of sessions. So 1 million sessions, approximately 1 million sessions in the switch are compared to approximately 1,000 sessions per core deployed on an x86-based server. The quality of service parameters, delay, jitter, and packet loss rates are optimal with the switch. And we know the switch provides us with the flexibility to modify packets and do some customized functionality on the switch using non-standard feeds. Another observation is how precise the timing information reported by the hardware. And we use that, as we said before, to measure the delay and the jitter. And also, so the programmer can free unused resource and customize the program in order to accommodate more session. So in our program, we were doing media offloading. If there are some resources that we can free, this will enable us to accommodate more media sessions, to relay more media sessions by the switch. This is because of the limited resources that we have in terms of memory in the switch and some other resources. And also, it's always good to avoid complex application logic. We know that this system is very simplistic as it is now, but it really shows the advantage of programmable switches in telecom or in media providers. So since we were able to do it like that, we didn't need to do any more complex application logic. Although for future work, we are improving it, considering also parsing some media-specific fields to make better decisions. Yeah, so that's what we have. And I would like finally to thank the NSF. All the activities that we have in the CI lab at the University of South Carolina are supported by the NSF. And this is my email, and this is my advisor's email, Jorge Crichigno. The full text for this paper can be accessed here, and this is the website for our group, so that if you want to see, we frequently organize workshops and some other publications, so all the information are there. Thank you, and if you have any question.
Well, thank you, Elie. This was a very clear presentation, so I have a lot of questions for you. All right, so I think it's very interesting that you kind of could take kind of this application and basically offload it to a programmable switch. I'm wondering what was just your general experience with kind of offloading this functionality into the switch. As you mentioned, there's the resource constraint in the switch. There could be other programs running. Did you have any specific? Was there any specific challenges in just getting this to work on the switch, or was it pretty, smooth, sailing from when you decided what your functionality is?
Yeah. As I said, because of the the nature of the relay server is just to accept that packet, modify the field, and doing nothing else. So we thought that it's really exactly what can the switch do without adding any more complex logic. So in terms of implementation, it was simple, but now we are working on extending more. So for example, what can we do with the signaling traffic? Mm-hmm. And that's also challenging because there are feeds in the application layer, and obviously we do not want to go up in the layer. What can we do related to security? We don't want to use the switch as a, as a generator for DOS traffic.
Sure.
There are other considerations such as minimizing the header sizes so that, we don't have to really relay the whole packet, because some of the fields might be, predictable. And this is very related to media traffic, to voice over IP, because we generate a lot of traffic and we only have a very small payload in them. So if we can try to work on that so that we optimize it as well. We are now currently, we just did this as a proof of concept just to see the advantages compared with the x86 base. But yeah, we are in the process of improving it and add more complex features that are specific to media. Because currently we are just using the 5-tuple, and these are, transport layers. So they can work on any application so far. So there's no much complexities when we deal with the specifics of RTP, for example, or RTCP. So this is where we are going forward. And I think it was interesting to implement this and see the results.
Mm-hmm.
Some challenges we faced include where we were doing the experiments, we tried first to measure the delay and the variations and all the other metrics on the end users. And because we are using, Linux-based systems, and, we don't have like a commercial or a production-grade traffic generator, we were not always getting the results that we were anticipating. Right. But we thought that the only possible option to do it with what we have in our lab currently is just to, measure directly inside the switch, and that will really exclude all the other noises introduced by the traffic generators themselves.
Right. Yeah, that's very interesting. I was especially I have a lot of questions. I have to try to order them, but I was very interested about that experiment that you had with kind of implementing this alongside switch.p4. And even with because switch.p4 is this huge kind of complex program that almost takes up the whole switch. And you still managed to do what it was like 32,000, 64,000, a large number of connections. Do you think, so that's kind of following up on my question about the challenges of kind of implementing this on the switch. Do you think there's going to be that is enough for a relay server? What is the typical load on a relay server?
Yeah, that's a good question, because we used RTP proxy specifically because it's being used with operators now. It's a production grade, and approximately per core, if we want to achieve the optimal quality of service metrics with a server based like x86, it handles around 1,000 to 1,500. That's with one core on a server. So really, if you want to scale it, then you have to add more cores, and you have to run these RTP servers or relays separately. So because, due to multi-threading, so you will have to run each instance by itself, and then each instance will able to, run 1,000, I would say, before we start getting a lot of losses and a lot of degradation in the performance.
Right. So you're basically you're saving a lot on the cores, right? If you wanted to do even 64,000 on this kind of servers, you would need a lot of cores, right?
You would save a lot, but most importantly, I think that with the switch.p4, it's interesting because it's a bit modular, right? So not all the time you want to use ACL or you want to use some other stuff. So you can always keep some complex functionalities for forwarding and some other data center related features, but at the same time, increase the number of sessions. And I think this is pretty easy to do it. I'm sure that you know about the switch.p4 program. You can easily customize it. So I think that once you are able to free some unused resources, you'll be able to accommodate much more sessions than what you would in a relay server.
Right. I mean, even 64,000 seems like still a big improvement, right?
Yeah, especially you are getting nanosecond or few millisecond
Right,
maybe, I don't
apart from the
know,
performance, right,
compared
like
to.
great performance, like even in terms of number, because so the reason I'm asking that is that that is kind of one of the biggest challenges when you're trying to upload something to hardware, right? Like the amount of state that you can just keep, right? So just, you know,
Exactly.
it's kind of a relief to have an application where you actually have enough state, you know, that can,
Right.
yeah,
And the thing is, like with our application, there is no way but to store some fields. You know, no matter
right,
how much you try to optimize. I mean, obviously we can do some further optimization that would require changing the SIP clients, but nobody wants that because you know the SIP clients have been in the market for 20 years maybe, and all devices use the same. You know, for SIP and RTP, they are very consistent. So we won't be able to modify the end users, and we have to uh, make it portable as much as possible. So there's no way behind or like around trying to save more
right,
state in the switch.
right, right, right. Right. And as part of your future work, you mentioned that there's a kind of extra stuff you're trying to do, which is specific to media traffic. And one of them, I think, was you said like not avoiding to copy some extra headers. Can you kind of explain a little bit about that more in detail? Like what is those extra
Sure,
headers? Like how are you going to do that?
sure. I mean, currently we are still investigating this. We don't have like a concrete idea how to do it, but there are some standards like ROHC, for example. This is for header compression, and there are some other also standards, but these are used specifically in RTP and in media traffic because, as I said, you generate a lot of packets and the payload is small. So if you can predict some of the headers, you know, in your network, like between your switches, if you are considered like a large infrastructure, an operator network, so you might have several switches, and you need to relay from user A to user B among, you know, several switches on the road. So if you can try to predict some of the fields in your headers, then it will of course save some bandwidth in your network.
What do you
We,
mean by
we still,
predicting? Like what kind? Like what kind of prediction? Like what is the headers? What are the headers that you're predicting here?
yeah. So there are some fixed fields in the RTP that we don't use.
Right.
Uh, and because this is our network or this is the operator network, you can, for example, agree on a single value and use that same value, you know, at the edge sides. You know, when you first receive and you first like
Right.
de-encapsulate and send it to the end user.
Right.
So you can work with that. There are some fields that are fixed and you don't need them.
Right.
So, and this is not like very new idea. As I said, there has been some standards on that,
Oh,
but
so
they
what
rely
you
on.
mean is that you could kind of take those out and, you know, just not have them cross your network and then at the edge, like kind of add them back to the packet. I see.
Right,
Save
right,
packets, right?
yeah. And because this is your network, you have the flexibility to do whatever like you want in it, as long as once the packet exits your network, the clients on the end users will still know, you know, how to do with it and how to, you know, reply back to that packet.
Right.
So yeah, we think that it's doable. We are not sure the advantages in terms of like numbers, how much it really improves. We are working on that at the moment.
So, but that's separate from the relay server functionality, right? So this doesn't need to be even close to the relay server. This can be just any network that is kind of a transit for media traffic. Am I right or am I?
Yes, you are right. You are right with that. With the relay server, because we are just like using it at the beginning to determine these ports and we are learning them and pushing them on the fly to
Right.
the switch, then it will just be used at the beginning of the session and that's it. But
Right.
after that, between the switches, yeah, we can do this kind of header compression or removing some
Right.
fields that we don't use, independent of the relay server. We don't go with the relay because the relay, you know, will get that whole packet, and we don't want to mess with the packet that's arriving to the relay. So that's why we just do it after the offloading functionality starts to work on the switch.
Right. Right. So this kind of, I think is a good segue for another question that I had about kind of the general vision you have about how this offloading is going to work. So I guess, if you're running a relay server, right, you're hosting it somewhere. So at least for the first set of optimizations that you've done, do you imagine that there's going to be a switch that is like directly attached to the relay server where this functionality is offloaded? So the switch that is actually keeping kind of doing the relay functionality, do you imagine it to be kind of co-located with the relay server, or could it be any switch in that kind of in the proximity of it? Like, what is your vision about how this would get deployed?
I think as long as you have a programmable switch, you don't have to worry where, like, if you place it very close to the relay server, because once that offloading function starts, we are not going at all to that server. So I think, yeah, in terms of placement, of course, it depends on the infrastructure of each network, but it can be easily generalized, I would say. Yeah, so the placement won't really, I mean, obviously we need it as close to the edge as possible. But I don't see a problem with, the placement. I don't know if I answered your question, if that was your question or no.
Yeah, I think I'm still, so I think I'm a little confused about how packets get, so when you have a relay server, right, the packets are addressed to the relay server. So at this, like in your proposal, do you envision packets actually being sent to, I mean, like the switch having an IP and the packets are sent to the switch directly, or is the switch actually snooping packets and doing the relay in the middle? Like, what is happening?
Yeah, actually it can be both. We use that way because it's easier to deploy and easier to interwork with the existing systems. And most systems nowadays have these relay servers where we use RTP proxy. There's other implementations. There are some, proprietary and some open source. To answer your questions, yes, it can work with, without even having a relay server at all, but then you would have to do some more complex stuff in the switch. We didn't see any value of doing that because really the relay server is just being used at the very beginning of the session. But also there's one additional observation to answer this question. There are there are some times where we need to do some lawful interception.
Right.
So the relay server is still useful on that side. So let's say we need to have some logic on the switch that says I need to intercept that call from or between these two users. You can program the switch to do that, and then you'll have to maybe mirror the traffic to your relay server, and the relay server will do all the processing, because most of the relay servers nowadays, they also perform some additional stuff besides modifying the fields. So you can, try to sniff the packets, try to filter per call, and listen to the call, try to do some enhancement to it. So you might still be using some of these for some specific sessions that you need to monitor. Yeah, but mainly, like the main usage of the relay server beside lawful interception is to solve the NAT problem. And some solutions nowadays, they don't even use the relay in case you don't have a lot of firewalls and NATs in the middle. So if you can reach the device directly, then you don't even need to go to the relay. But that small part that goes to the relay will have a very low performance compared to having it peer-to-peer or like end-to-end.
Right. So do you think, you said there's like extra stuff that the relay server is doing. Do you, and I think you kind of answered this, but I just wanted to be clear on that. So do you think there's going to be value in trying to offload those to the switch, or are they too complicated and maybe not that kind of frequent for it to be kind of valuable to be offloaded to the switch?
I don't think that there will be much value if we offload some complex stuff, like try to modify the, obviously some stuff cannot be offloaded to the switch, like when you deal with trying to do some noise cancellation or some stuff like that. If you want to go to the payload, this is not doable in the switch. So yeah, I don't know about the features that's are being implemented now in the relay in terms of improving the media in terms of quality. I don't think you can do it in the switch in terms of do some signal processing on the audio.
Right.
So that's what I
Right.
that's what I think. But there might be some other functionalities that can be offloaded. For example, we are looking now at conferencing, which is a big issue now. You can see that all the solutions that are there, once you increase a certain number of participants in the conference,
Right.
they will you will need to pay. And the reason is that because we are doing mixing on the server, so you mix several RTP streams and then you transmit them to the other participants. So here the switch might add some functionality, and we are also working on that as well.
Oh, that's very interesting. Yeah, that would be very useful for
Yeah.
sure. Yeah. Right. Yeah.
We have to find like a middle ground, because doing mixing on the switch is also not possible. Mixing will do by doing some operation on the payload. So if you have several payloads, you do some operation to have the final audio, and that will be like the one that everyone will hear in the conference. This
When
is
you
also
say
not possible.
operations on the payload, is it like you have to do something on the entire payload, or is it possible to kind of only parse a little bit into the payload and do some optimizations or do some part of the processing?
Yeah, I don't know. I cannot answer that. We didn't start yet with it, but like current mixers with conference servers, they try to have like bit by bit addition, so that you can try to have several callers having one stream, and that stream will be sent to the other participants. And for example, it will subtract yours so that you don't hear like yourself when that audio is being sent. So if you are to do this on the switch, then that will be a little bit complicated. But there are other possibilities. So that's one model for conferencing. You can use other models for example, if you try to do the mixing on the end devices, right? So it's like you are relaying, let's say, 10 media sessions for that same device, but the device will do the mixing. So there are some other, I think, areas to go into. But every area has its own limitations, especially with the conference. We thought about some of them.
Right.
Yeah.
Right. So actually, I have a follow-up question here. So I think a lot of the stuff that you said that the switch cannot implement, it looks like, I mean, they would actually benefit from some acceleration, but the switch is limited and won't allow you to basically perform that acceleration on that traffic. So have you actually considered using programmable NICs instead? So actually adding programmable NICs to your server, because you would get some more flexibility into kind of what kind of functionality you want to run, or kind of doing more complicated stuff.
Right. Yeah. We haven't started yet with the programmable NICs, but as you said, we thought about this, and it can indeed improve the performance. We just didn't start yet on it, so I don't know if there are some added values, when we compare like using NICs on x86 based server versus having switches. I don't know really, but yeah, we are also investigating that.
Yeah, I would imagine, I mean, and programmable NIC would be a good middle ground. I mean, for sure, like a switch has is much faster and has much like higher capacity,
Right.
but at the same time is much more limited because of that. So
maybe a hybrid approach, for example.
Yeah, a hybrid approach, like you can keep the kind of NAT traversal stuff in the switch.
Yeah, like if you want to relay media normally without doing any more, additional computation, just use the switch. In case you need to do some more, then relay to the server and use the NIC. Yeah, it's like a hybrid maybe of two.
Right. All right, I think that is all my questions. I don't know if you have any final remarks or thoughts.
First, thank you for accepting this work and letting us being part of the P4 Expert Roundtable series. I'm very interested to see the other work as well. I've seen titles and they're very interesting.
Right.
Yeah, and I think it's a pretty good initiative, especially that we were able to run it virtually. I just hope that everybody stays safe with this, this pandemic, and yeah, I'm looking forward to see the other work and to maybe contact the other authors and see if we can collaborate.
That's great. It was a pleasure having you. Thank you
Thank
so
you.
much.